Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of graphs of polynomial functions for a college algebra student. And you should have watched videos so far in this list of videos concerning graphing quadratic functions, graphing power functions, knowing about the end behavior power functions and polynomial functions, recognizing characteristics of graphs of polynomial functions, and using factoring to find zeros of polynomial functions. Now we're going to go in a little more detail about those zeros. Remember, again, that a zero of a polynomial occurs at a number, let's just say, since C is being used on this page, let's go ahead and just say that we have a zero at k if f of k is equal to 0. That implies k is a 0. So, and we also had mentioned in the last lecture that if you have a 0 at a number, for example, we have a 0 at k here, that means that x minus k must therefore be a factor. Or actually, really what we said was that if we have 0 at x equals k, then k is an x-intercept for the function. And we're about to discover that means that x minus k is a factor. But let's go ahead and just do that. So it's kind of a discovery-based example. So we're going to use Desmos to graph this polynomial here. Notice that I didn't actually give you concrete values for a, b, and c, or d. We're going to play with those. So we're just going to use Desmos to graph that polynomial for different values of the coefficient a and then different values of b, c, and d. And finally, we're going to go ahead and change the powers of these. And we're going to talk about what the effect of those changes are. So let's go ahead and move over to Desmos. Again, it's my goal to make sure that people know how to use technology like Desmos. So I'm going to show you how I would do this. P of x is equal to a times the quantity x minus b times the quantity x minus c and quantity squared, and then times the quantity x minus d. And quantity cubed, I think is how we had it. Yeah, I'm looking over at the page here. And notice that when we do that, it asks us to add a slider for each of those values, a, b, c, and d. In this case, we would call those parameters. So we're going to add a slider for all those parameters. Right now, all their values are set to 1. I'm going to adjust b, c, and d to not equal 1 because it's not very instructive to actually allow b, c, and d to all equal 1. So how I'm going to do this is I'm going to go ahead and adjust what a can go, or not a, I'm sorry, what b can go between. So I'll adjust b to go between -10 and let's just have it go between -10 and maybe -5. And I'll have it go by steps of 1 just because it's more instructive to do that. And C, I'll have it go from, let's go from -3 to +3, again, step sizes of 1. And D, I'll have it go between, let's say, a +5 and a +10. Again, step by 1. So I just don't want these to be the same value is my main concern. Another thing I'm going to do is I'm going to adjust this grid to not have actual grids on it, and I put it in projector mode. Now, that being said, let's take a look at the effect of our choices of B, C, and D. If I change B, right now B is at a -5. Let me zoom out so you can see the entire -10 to 10 area. Right now B, x equals B is set to -5. So x minus B is one of our factors here. Notice what happens as I move that. Notice it's actually moving the x-intercept that's occurring. Right now it's at -5, but if I move b to be a -6, notice that our x-intercept ends up being a -6. And if I moved it to a -7 or -8 or -9, -10, this kind of justifies in a way, it's not a proof, but it gives you a visual justification that B, this B right here, must be some type of x-intercept for our polynomial. Let's see if that holds for C and D. Right now, we have C set to equal 1, and if you look over at our graph, yeah, sure, it looks as though it has an x-intercept at x equals 1. If I move this over to 2 or 3, the value of the x-intercept changes accordingly. If I move it over to 0 even, right? And I can go in the negative direction, -1, -2, -3. So it looks as though, again, even if it's x minus c being squared, that c plays, again, the role of an x-intercept. And finally, the b value, the d value right here, well, right now we have that set as 5. And if you look at our graph, yep, it's crossing at x equals 5, or intersects the x-axis at x equals 5. If I move that over to 6, it sure will follow that advice and move over to 6, and so on and so forth. So you should be able to conjecture that the roles of B, C, and D are that they tell us the x-intercepts. And that should just make sense, because if you think about it, you have x-intercepts when our function turns into 0. So if I were to plug in, for example, into our polynomial, the value of b, we would get a times b minus b times b minus c squared times b minus d cubed, but b minus b is 0, and 0 times anything else is 0. So when we plug in the value of b for the x value, we get an output of 0. That is, b must be an x-intercept. So that should make sense to you. Also note if b were negative. So I'm going to write this down, but I'm going to erase it very quickly. But if you had something like p of x is equal to x plus 4 times x minus 2, it would have x-intercepts at x equals 2, because this 2 right there. Basically, you're asking what would turn each of these factors off. Well, 2 would turn that factor off, and -4 would turn that factor off. So therefore, the x-intercepts here are 2 and -4. Essentially, whatever is the opposite of this number, or whatever just turns off this entire factor, that is the x-intercept. So that's the lesson to be learned just from the B, C, and D parts of this function. So we played with that. And then the second part is, well, what if we were to change the coefficient a? Well, we kind of know what happens from transformations of functions, but it might be nice to see it. So let's go ahead and hop back over. Now, something I want to say here, if you're asked to graph something by hand, that's exactly what you should do, because when people copy from Desmos for their graphs, it's incredibly obvious. So please be aware, when you're asked to graph by hand, you should graph by hand. Don't use Desmos to help you, because it will be incorrect, honestly. Anyhow, if you increase the value of a, not much is visible here, and that is generally true for all polynomials, that as you increase the value of a, you don't get to really see what's happening because it's very subtle. What does end up being somewhat not so subtle is when you decrease the value of a nearer to 0. So remember, from transformations, if you multiply your function, because a is the coefficient, by a number less than 1, you're actually compressing it towards the x-axis. If I zoom out, it doesn't look like it's compressing it, but it actually has compressed it. It's very difficult to see. So anyhow, the other thing I should note here is if you allow a to go negative, so all of a sudden it flips when you go negative. And so that's just a little note. We know that a, being the lead coefficient, ends up either stretching or compressing the graph. And if it's negative, it is going to rotate or reflect the graph about the x-axis. All right, what else were we asked to do? And this is me just writing down exactly what I just said, by the way. If the absolute value of a is greater than 1, then you're stretching that graph vertically. If the absolute value of a is between 0 and 1, you're compressing it vertically. And if a is negative, the graph is reflected about the x-axis. Now, the final piece that I'm asking us to do, and this is kind of the most important piece for me, is to change the powers and see what happens. And this is actually going to be critical in this section or in this lecture. So here we're back to the main Desmos screen. Notice that I have my x-intercepts at -9, 0, and +9. I just wanted them spread apart a little bit so that we can talk about each individually. And what I'm going to do is actually change these powers. So I'm going to raise this one to the power p. I don't know if I could do this, but I'm going to, yeah. I was going to say, I don't know if I could do this and call it p sub 1, but I can. So we'll raise that to p sub 1. This will be raised to p sub 2 power. And we'll finally do this one to the p sub 3 power. And we're going to go ahead and add some sliders into those. And because they're polynomials, you cannot have negative power. So I'm going to have those powers go from 1 to, let's say, 12 step sizes of 1 on each. So again, this one will go from power of 1 to 12, step size 1, and the last power will go from 1 to 12. Again, step size of 1. Now, our original polynomial had powers of 1, 2, and 3. Power of 1 on x minus b, power of 2 on x minus c, and power of 3 on x minus d. Let's go ahead and just change the power of p sub 1, so the power of x minus b. Let's make that a square instead. Now, notice that it seemed to have cut off the graph, but that's not actually what happened. If I zoom in far enough to this, you will see, and it actually takes quite a bit of zooming in because of the fact that this curve is so wild. But if you zoom in enough, you'll see that it looks like a parabola. Notice the power's 2 on that factor. And if you zoom in close enough, it looks like a parabola. Now, since I'm zoomed in, I'm just going to increase that by 2 powers. Let's go with even powers. Now, notice what happened. I went to 4 powers on that, and it doesn't look like it did. It looks like it's a flat line, but that's a lie. If I zoom out enough, you will see that it still looks like a parabola. It's just not wider, honestly. It's actually flatter. Again, let me bring it down to 2. It looks wider, but it's actually flatter. Let me get back to 4 there. If I go to a power of 6 on that x minus -9, so right now it's x minus -9 to the 4th. Let's go to the 6th power. I have to zoom out, and you'll see it still has that parabolic shape, but it's really flat near -9. If I go to the 8th power, again, same parabolic shape. It's just flatter for longer around -9. If I go to the 10th power, again, same basic shape, but flatter for longer around -9. And then the 12th power, same basic shape, but flatter for longer around -9. So the basic idea here that I'm trying to drive home is that if the power is even, it's going to look like a parabola. In fact, let me change this one just to have even only powers so I can do that. There we go. So it's going to look like a parabola near those even powers. And let me zoom in just to showcase that. Again, we saw this earlier, but whoops. Hold on. Sorry about that. I don't have the clicking thing on my mouse here. There we go. That keeps it from going wildly. If you zoom in enough, it is parabolic. If you, again, pop it up by 2 more powers, it's still even power and it still looks parabolic. It's just flatter for longer. That flatter for longer idea is super critically important for us because that gives us an idea of how to graph near to zeros of functions. Now I'm going to zoom out. By the way, that argument of even powers, notice x minus c raised to the p2. Right now I have p sub 2 being an even power. That should look parabolic if I zoom in enough. And let me just zoom in. You notice I have to zoom in quite a bit here. In fact, this time I will just click off my thing. There we go. You can see totally does look like a parabola. If I increase it by 2 powers, it now does look like a parabola. But I have to zoom out to see it. Notice it's not like it's super duper flat for a long period of time. It's only super flat for a short period of time. If I go up 2 more powers, it's flat for a longer period of time. So same idea. 2 more powers, flat for a longer period of time, and so on and so forth. But what if I wanted to do this one with odd powers? So let me go ahead and fix the step size here. I'll go from 1 to 13, and I'll do it in steps of 2, so it's only odd numbers. Now, if you look at this power of 1 on x minus c, and remember c here is, what do I have c at? 0. So x minus 0, or in other words, x to the power of 1. Well, what does that look like? If you zoom into it, it will look, and you have to zoom in for quite some time with Desmos. And in fact, I don't even know if it'll ever fix it. Nope, doesn't look to be doing that. So I should probably just stop, but I'm super fascinated with doing this now. But it'll look like a line if you zoom in enough. It is a line. It's just Desmos can't quite capture it. So what if I go up to the power of 3? So let's try that. Power of 3 on this. There we go. And let me zoom out to show you what this looks like with the power of 3. I have to zoom out for quite some time here, just because I zoomed in for quite some time. So let me just do that. By the way, if you think that I'm zooming out to large numbers, I'm not. I'm not even to a size of 1 here. So there we go. Power of 3, and notice it looks very cubic in shape. Cubics actually start low and go high, but this is just by the nature of the function we're dealing with. It just happens to be starting high and going low. But the main thing that you need to note here is it looks cubic in shape. If I were to maybe increase that power to the next odd and zoom out, it still looks cubic in shape. It's flatter for longer. If I go up to 7th power, it's still cubic in shape. It's just flatter for longer. 9th power, still cubic in shape, flatter for longer. 11th, and then 13th. So they're all like this basic shape. If you're odd exponents, they're all, well, I shouldn't say all odd exponents. It's true that if your exponent is 1, it's just like x to the first, or a line. But any odd power above the power of 1, and it's going to look like a cubic. And you can see that if I scroll over, I have to actually zoom out for this, but if I scroll over to x equals 9, here's, where's 9? Right down here, that's D. Right here. So we have x equals 9, and its power is supposed to be cubic, but you don't see it. It doesn't look like it's cubic through there, but that's just because we're not zoomed in enough. If you zoom in enough, it is actually cubic. You can see it sort of happen here. That's as far as Desmos will allow me to zoom in, by the way. So it is cubic. Now, if I zoom out and I go ahead and maybe raise that 3rd power to the next odd number, so I'll go from 1 to 13 in steps of 2. Let me go to the next odd power, which is 5. You can see, yep, still cubic. It's just flatter for a longer period of time. Again, if I change that power from a 5th power to a 7th power, still cubic, just longer period of time in that it's flatter. 9th power, still cubic, and then 11th and 13th. So the punchline here is odd powers look like cubics, even powers look like parabolas. The higher the power, the flatter it is for a longer period of time. And so I've added that note here. Odd powers look like cubics, and I should put on the extra word here, locally, because it's not true that they actually look like cubics throughout the entire graph. It's only locally near the 0 in both cases. So if somebody were to say, for example, I want you to graph p of x is equal to, I'll just leave the lead coefficient as 1, and let's say we're asked to graph x plus 4 to the third power, x minus 3 to the sixth power, and x minus 10 to the, let's make this to the 17th power. Now, first thing I should note here, when you're graphing all the way up to this point in mathematics, you've probably been asked to graph intercepts. And in this case, that's almost exactly what you'll be doing. There's one intercept you will never really truly want to graph with polynomials, and that is the y-intercept. It's not that you're not going to graph it, it's just that you're not going to graph it exactly. Because think about it, if x were 0 here, you'd have 4 to the third times negative 3 to the sixth times negative 10 to the 17th power. That is massive. It's worthless to even try. And this is why it's easy to tell when somebody copies something from Desmos, because all their graph looks like is a bunch of lines. That's not what I want to see. So let's go ahead and plot out the x-intercepts. So the 0 from that factor is going to be negative 4. The 0 from that factor is a 3. And the 0 that turns off that factor is a 10. Those are our x-intercepts. I'm going to draw those in blue. So let's just pretend as though that's negative 4. And let's pretend as though this is positive 3. And this is 10. Now, the other thing I need to kind of draw on here is the y-axis. Even though I'm not going to legitimately try to graph exactly where the y-intercept is, what I do want to do is ask, is the y-intercept positive or negative? That's all I really want to worry about. So let's go ahead and ask ourselves if p of 0 is positive or negative. Well, it's a positive number cubed, so that's positive. And then when you plug 0 in here, that'll be a negative number to the sixth, which is still positive. So we have positive times positive so far. And finally, if you let x equal 0 in this last factor, you have negative 10 to the 17th, or in other words, a negative number to the 17th, which is a negative. And this will equal a negative number. So I happen to know that our y-intercept is probably way down here, but I don't really care about what its value is, so I'm just going to mark it right around here. The scale is not that important to me. What is the behavior near to the intercepts. So let's take a look at the powers here. And now that I'm saying let's take a look at the powers, I'm going to introduce a little bit of language. These powers on these factors, we would call, well, okay, first of all, the factors are associated with the zeros. So I'm going to start by saying these are the zeros right here. The powers on those factors, we would call the multiplicities of the zeros. So for example, the 0 of negative 4 has a multiplicity of 3. The 0 of positive 3 has a multiplicity of 6, because that's a power on x minus 3. And the 0 on 10 is 7. The multiplicity of the 0, 10, is 17, because that's the power on the factor x minus 10. This multiplicity allows us to say, okay, so near to the 0 at x equals negative 4, it's going to operate sort of like x cubed, sort of. And near to the 0 at x equals 3, it's going to sort of look like an x to the sixth. And near to the 0 at x equals 10, it's going to sort of look like an x to the 17th. Each of those, we're just going to consider, are they even or odd? And if they are odd or even, then how high is the power? All right, so for example, the 0 at negative 4. What I'm going to do is I'm going to start at the y-intercept here. It's going to want to be dragged like a magnet to that 0 at negative 4, x equals negative 4. And the multiplicity of that is 3, right there. So I happen to know that it's going to look like a cubic going through. So I'm going to have this ink climb up here, but as it goes through, it'll have this kind of, it'll have this really nice cubic behavior. I have a habit of going in the other direction, so let me just have it like that. Now that looks very cubic in nature going through that. I also know it's not going to come back down, so I'm just going to have it go up forever here. It's not going to come back down, by the way, because there's no other x-intercepts. So I know that's what it looks like. Now let's look at x equals 3. That's a 0 of multiplicity 6th. So it's going to look like x to the 6th power, roughly. When I say roughly, there's a plus or minus piece on there, which means that it could be upside down or right side up. Well, the fact is, since I'm approaching x equals 3 from the below, it's going to be upside down. It's going to touch, it'll be flat for a little bit like that, and then do this. So it looks sort of like that. Notice I'm showcasing how flat it is right there, because it's a 6th degree, or a 6th, the multiplicity of that 0 is 6. So it looks like x to the 6th, which is pretty flat as far as parabolas go. So then it falls for a little bit, but like a magnet, it'll be drawn right back to coming to x equals 10. X equals 10 is a 0 of multiplicity 17. So that's a super high odd power. So it's going to be very, very flat near x equals 10. And it's going to be cubic in nature. Very, very hard to actually capture that, but it looks something like that. And notice that is pretty cubic in nature. Now, the painful thing here is that you will not be able to check your work using Desmos, because Desmos cannot graph this the way we can graph this. So one thing you can do is you could look at the ultimate overall power of this polynomial. 3, if I multiplied out that first factor, I'd get x to the 3rd. If I multiplied out the second factor, I'd get x to the 6th. Well, x to the 3rd times x to the 6th would be x to the 9th. And you can see what I'm doing. I'm just adding these powers. And then if you were to wish pain upon yourself, you can multiply out that binomial 17 times to get x to the 17th and a bunch of other stuff. But x to the 9th times x to the 17th would be x to the 26th power. And that's an even power, so the end behavior should be like a parabola, up and up. Because again, it's like an x, roughly, very roughly like an x to the 26th power, with a positive leading coefficient. And that's a pretty good sketch of this polynomial with proper behavior near the zeros. That's critical. You want proper behavior near the zeros. Don't just draw a line through. That it would be wrong, period. Lines are reserved for if you have a 0 of multiplicity 1. It acts like x to the 1st. But when it's not a multiplicity of 1, then you should have appropriate behavior there, whether it's cubic or parabolic. Now, I sort of jumped ahead a little bit in my lecture, mainly because I've taught this for so long, I happen to know kind of where we're going. But we've mentioned this, but it's good to have it in a theorem. If you know you have a 0 for your polynomial at x equals c, then x minus c must be a factor. That is, if you know that p of c is equal to 0, then p of x, the original function, must be like x minus c times some other stuff. X minus c has to factor out if c is a 0. And that should make sense, because if you take a look at this new polynomial, plug c into it, you would get c minus c times q at c, q being just the rest of the polynomial after you've factored out x minus c. Well, c minus c is 0. 0 times anything is 0. So it does kind of work with this statement right up there. P of c is 0. Well, that's what we just found out. This topic, or this idea, this theorem, is actually proved in a pre-calculus course because you need more advanced concepts than what we deliver in a college algebra course. However, this topic is incredibly powerful, because if somebody tells you, oh, you know what, that my polynomial has a 0 at 5 and 10, then I know x minus 5 is a factor of my polynomial, and x minus 10 is also a factor of my polynomial. It's critically important that you're able to make that connection and do that Very, very, very important. And where we're heading to next is, again, something I've already sort of stated here. If you have a polynomial and x minus c to the power of p is a factor of it, and if it's the greatest such factor involving that expression x minus c, then we say the associated zero has multiplicity p. Now this is kind of important to talk about. So if I handed you a polynomial, let's just pretend, and the polynomial was, I'm going to have it pre-factored just for this conversation, x minus 1 squared times x plus 2 to the third times x minus 1. The 0 at x equals 1, first of all, I'll just say x equals 1 and x equals negative 2 are zeros. That's by definition. If you plugged in 1, this whole polynomial would turn into 0. If you plugged in negative 2, the whole polynomial would turn into 0. It's also true, that statement, because of our last little theorem. X minus c being a factor implies that c is a 0. In fact, this really is an if and only if. The way I've written it, I wrote it as if one is true, then the other is true. However, it should actually be the following. C is a 0 of a polynomial if and only if. So let me write that with this ink here. If and only if. So it works both ways. So if you know x minus c is a factor, then c is a 0. And if you know c is a 0, then x minus c is a factor. But anyhow, we're using that idea here. So I'm saying, suppose that you have this polynomial and it factors like this. Then 1 and negative 2 are zeros. The multiplicity of the 0 for x equals 1 is not 2. It's the greatest such power of x minus 1, the factor x minus 1 in this polynomial. And if you were to write this appropriately, it would be x minus 1 cubed times x plus 2, whatever I said, cubed there as well. So really the multiplicity of that 0 is 3, and the same thing actually here. The multiplicity of this 0 is also 3. And that's what this definition is saying. If you have x minus, I'll use these numbers, x minus 1 to the third is a factor of the polynomial. And if there's no other way to increase that to x minus 1 to the fourth, then we say 1 is a 0 of multiplicity 3. Right. Not a big deal, but well, the idea is huge because you will use this idea for the rest of mathematics. So you need to get used to this. So let's take a legit example here. State the zeros and their multiplicities for the following function. Again, we're going to also state the degree of the overall polynomial, or maybe I should say the overall degree of the polynomial. Remember, you can find the zeros by factoring the polynomial. Well, this is pre-factored. I just want to mention one thing here though. It is pre-factored, but that x is the same thing as x minus 0. You would never really write it that way, but it is true. And another thing I should mention here is that our previous theorem that if c is a 0, then x minus c is a factor. And if x minus c is a factor, then c is a 0. That theorem relied upon x having a lead coefficient of 1. And unfortunately, this middle factor here does not have a lead coefficient of 1. We can force that if we want. It's a very long-winded, well, it's not long-winded, but it's a longer process than needed, but I'll show it anyway. So right now, I'm just rewriting this polynomial as 1/2 times x minus 0. And then what I'm going to do is I'm going to divide 2 off of both this x and this negative 3. Again, normally you wouldn't go about it like this, but I'm showcasing the logic as to why it works. Now we have a law of exponents we can use here. This will be 2 to the third power, or 8. So I'll take that 8 and I'll move it out in front. 8, 1/2 of 8 will be 4. So we have 4 times x minus 0. And we have an x minus 3/2. And that's raised to the 3rd power. Then we have this x plus 4 raised to the 6th. And then we can actually, from this, we're staring at the zeros and their multiplicities. I'll make a little table here. 0 versus its multiplicity. We have a 0, x equals 0 of multiplicity 1. We have a 0 at x equals 3/2. Multiplicity 3. Again, that's just from this. We have a 0 at -4. And it has multiplicity 6. Now, to be honest with you, this is not how I would go about finding the zeros and their multiplicities because it's a little long-winded. Instead, it's much easier to ask the following questions. I have this polynomial. I would like to find the zeros. Luckily, they've factored it for me. So, here's the first factor. What would turn that into 0? Well, that's a pretty easy one to answer. X equals 0. And what's the multiplicity? In other words, what's the power? 1. All right. What if I instead asked about this guy? What would turn that into 0? Well, 2x minus 3 is equal to 0 when x is equal to 3/2. And what's the power? In other words, what's the multiplicity of that 0? 3. And finally, on the last one, again, what would turn that into 0? X equals -4. Oops, didn't mean to write in that ink. And what's its multiplicity? 6, because that's the power. Notice I have the same exact answer. So I'm just letting you know that the way I did it the first time, the first way through, was just to kind of give you the theoretical development. But to be very honest with you, nobody does it that way. We all just look at the original polynomial and ask ourselves, what would turn each factor here into 0? What else were we asked to do? State the zeros and their multiplicities. Done. Additionally, state the degree of the polynomial. Well, if you were to multiply out this polynomial, bad idea, but if you were to do it, you'd have x to the first from that, x cubed eventually from that, and an x to the 6th, again, eventually from that. No, remember, powers do not distribute through binomials. You'd actually have to take 2x minus 3, multiply it by itself 3 times. So you'd have this big, long polynomial. Same thing with x plus 4 to the 6th. You'd multiply it by itself 6 times. It's a big, long polynomial. You don't want to do that. So it's much faster just to say the overall greatest power on our variable in each case is going to be 1, 3, and 6. And then when you add those powers using the laws of exponents, you'll get 1 plus 3 plus 6, or 10. So the overall degree of this polynomial is 10. And that's how we note it down there. Degree of p is equal to 10. Another way you could quickly find the degree of the polynomial is to add the multiplicities of all the zeros. It's the same thing. So I build the table to showcase the zeros and their multiplicities so that I can also quickly state the degree of the polynomial. That will be very powerful and helpful for us later on. This is yet another theorem that I've kind of already alluded to within this lecture. The behavior of a polynomial near to a 0, where the 0 has multiplicity p, mimics that of plus or minus x minus c to the p power. Now, if you think about the original problem that I've set up here and we went through, I was stating, oh, you know, x equals -4 is a 0. It has multiplicity 3, so it acts like roughly a -x cubed. It does still act roughly like a -x cubed. However, it's more like a shifted -x cubed, because a -x cubed actually looks like this. That's because the x cubed has not been shifted. But in reality, it acts honestly like a roughly an x minus, what's our 0? -4. So an x minus a -4, which is x plus 4, cubed. Now, nobody's really going to ding you on that. It's just, it is, to be theoretically rigorous, it is true that it honestly acts not like x cubed, but like x plus 4 cubed, a shifted cube. We took that cube and shifted it 1, 2, 3, and 4 units over. But I wouldn't really worry about that. The most important thing there is that it looks like a cubic. So in this case right here, I think most people who teach would not include the minus c there. They'd just say, oh, it looks like x to the power. And it is sort of true. It's just been shifted. Okay, but locally it looks like x to that power. All right, in this next example, you're handed a polynomial graph, the graph of a polynomial function, and you're asked to identify the zeros and state their possible multiplicities, and then give a possible equation of the function. So if I'm looking at this, I can easily see the zeros because I've labeled them, and I'll make a little table of values here. Right? 0 versus its multiplicity. And the zeros are at -6. 0, remember 0 is also an x-intercept. And 4/3, and then finally 4. I can see it from the graph right there. And now let's just discuss the possible multiplicities. Well, this one, if I zoom in enough, man, it looks cubic, but it could be the 5th power, honestly. So it's a little bit tough to get that perfectly. It's either 3 or 5, though. Some people would argue it might be 7, but I'll just keep it at about 5. And then if you look at the multiplicity of the 0 at x equals 0, that looks like a parabola. So I'm just going to go ahead, and it doesn't look flat. So I'm going to say the multiplicity of that is 2. If you look at the 0 at x equals 4/3, that goes through not like a cubic, but like a line. So that's going to be multiplicity 1. And finally, at x equals 4, now this is like a parabola, but notice how flat that is. It's flat for a while. So it's not going to be like an x squared, because that one's like an x squared. It's going to be more like an x to the 6th, maybe. And again, this is more of just a guess. So it's not like there's a perfectly correct answer, but I'm going to say it's probably about a multiplicity of 6. So those are our zeros and their relevant multiplicities. Now we're being asked to throw together a possible equation of the function. Well, let's start. P of x. I'm going to leave a little bit of space in front of everything because of something here. Let's start with the 0 at -6. So x minus a -6, which is x plus 6, should be raised to the 5th power. X minus 0, or x, should be raised to the 2nd power. X minus 4/3 should be raised to the 1st power. And then x minus 6 should be raised to possibly the 6th power. Now, we need to figure out a couple things. One, maybe somebody doesn't want fractions in their answer. If that's the case, you can factor a 1/3 out of both of these terms. And remember, factoring is the same thing as dividing. So if you had 1 and you're 1x and divided by a 1/3, that would become a 3x. And if you had 4/3 and you divide it by a 1/3, that would become a 4. So if I pulled a 1/3 out into the front of this entire polynomial, I would be left with x plus 6 to the 5th power, x squared. Let me clean that up. That was supposed to be an x squared. And then we have a 3x minus 4, that's to the 1st power. And finally, an x minus 6 raised to the 6th power. I'm going to erase this just to get it out of my way because it kind of is disturbing visually. The last thing I need to do is double check that it's opening in the right direction, because right now it's actually not. Look at the overall degree of this polynomial. That is, add up the multiplicities. 5 plus 2 is 7, plus 1 is 8, plus 6 is 14. If you think about a polynomial of degree 14, its end behavior, which is something we've talked about, should look like this. In between, we don't know what it looks like, but it should look like a parabola at the edges. But that's not what our graph actually looks like. It looks like the upside down version of that. So the way that we've written our function is not exactly correct. We'll need to throw a negative in front of these, or as a lead coefficient, because that would force it to be an upside down parabola over the long haul. So as you zoom out, it would be an upside, instead of going up, up, it would then go down, down, because it's reflected about the x-axis. So that's how you would build a polynomial function to represent a graphed polynomial. And to be honest, I think that this lecture has gone long enough, and I've kind of hit all the major high points with, at least with identifying zeros and their multiplicities. So let's go ahead and pause here. And on the next video, we'll talk about graphing polynomial functions in general.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.